This is the inside of a boiler furnace. Here, water tubes lining the walls of the furnace absorb heat from burning fuel. The water in these tubes is heated to the boiling point, producing the steam that drives the turbine. The specifics of steam production will be the subject of this program. You'll remember from the last unit that the boiler, along with the turbine, generator, and condenser, make up the steam cycle. Combustion in the boiler furnace produces hot gases, which heat the water in the water wall tubes. Part of the water in the tubes turns to steam, which is sent to the turbine. As steam passes through the turbine blades, the turbine shaft rotates, causing the attached generator to rotate, producing electricity. Steam that is passed through the turbine is sent to the condenser. Here it is cooled and condensed back into water. The water is then returned to the boiler, where the cycle is repeated. Now, from here on, we'll concentrate our attention just on boilers. We'll see how the most common types of boilers work. We'll see how combustion takes place. We'll follow the different flow paths through the boiler. And finally, we'll see some of the basic principles of boiler operation. We'll start with the water flow path in a typical drum boiler. This is a natural circulation drum-type boiler. It's typically 150 feet high or higher. One of its distinguishing characteristics is this drum. This is where feed water enters the boiler. It's also where the steam produced by the boiler is collected and sent to the turbine. We'll use this schematic drawing to trace water flow through the boiler. But first, let's take an overall look at the boiler. The furnace is here. Combustion gases flow this way and out the stack. The drum is here. Heated feed water is pumped into the drum here at the feed water inlet. Water inside the drum continuously circulates through downcomers to the lower headers. Now, for simplicity, we've shown only one downcomer and one lower header. In practice, there are usually two or more of each. The lower headers supply water to the water wall tubes. In the tubes, heat supplied by combustion in the boiler furnace turns some of the water into steam. The mixture of water and steam then enters the boiler drum. Once in the drum, the hot water and steam are separated by moisture separators and dryers. The steam collects at the top of the drum. The water is directed to the bottom of the drum. But how does the water get from the lower header back up to the drum? Well, we haven't shown any pumps that would force the water to flow up through the boiler tubes. The way that water completes this circuit from the drum to the lower header and back up to the drum is a second distinguishing characteristic of natural circulation drum-type boilers. Now, the key words here are natural circulation. And the key to natural circulation is the fact that cold water weighs more than hot water or steam. Whenever water is heated, the water becomes less dense. This makes it lighter. So for a given volume, hot water weighs less than cold water, and steam weighs less than either of them. In the boiler, water and steam in the water walls are hotter than the water in the downcomers. Why? Well, because the water walls are heated by the burning fuel. Now, since this water-steam mixture is hotter, it's also lighter than the water in the downcomers. The result is that the hot water and steam mixture gets pushed along by the heavier, colder water behind it. Then, as the colder water gets heated, it also becomes less dense or lighter than the water behind it. A self-sustaining flow is created. Natural circulation will usually continue on its own as long as water is available and as long as heat is produced in the furnace. We can demonstrate natural circulation with this lab setup. This glass container will serve as the boiler drum. This tube will be the downcomer. And this one will be the water wall tube. With the temperature the same throughout the system, we'll inject some dye and check the flow. With no temperature difference, there is no flow. The dye just settles at the bottom. Now, let's see what happens when we heat the water wall tube. In a real boiler, direct flame never touches the tubes. That would cause them to overheat and burst. But we have to use direct flame here in order to get enough heat to boil the water. Now notice what's happening. The water where we're applying heat is starting to boil. As the water boils, we begin to get flow through the system. You can see the dye moving up the water wall tube. The heated water is now overflowing the top of the tube. Simply by heating the tube, we've created flow in the system. This flow is just like the flow in a natural circulation drum-type boiler. Circulation in a boiler is necessary for two reasons. Now first, it provides a constant supply of water to be turned into steam. And second, it carries the intense heat away from the water wall tubes. If flow were reduced or cut off, the water wall tubes could overheat and rupture. Now here's a tube that did exactly that. It's a clear example of just how important continuous circulation is. Natural circulation is affected by three factors: the amount of heat produced in the furnace, the height of the boiler, and the pressure at which the boiler operates. The first two of these factors, heat and height, have a positive effect on natural circulation. Now, if you raise the temperature in the furnace, the natural circulation flow also increases. There's a greater temperature difference between the water walls and the downcomers. And likewise, the taller the boiler, the greater the natural circulation. Increasing the height of the boiler increases the weight difference between water and steam in the tubes and the water in the downcomer. The third factor, pressure, has a negative effect. As pressure increases, natural circulation flow decreases. Now this is because increasing the pressure decreases the density difference between steam and water. These factors that affect natural circulation are all part of boiler design. Each boiler is designed to be a certain height and to operate at a certain temperature and pressure. As an operator, you don't directly control natural circulation. You do, however, promote natural circulation by maintaining the boiler at design pressure and temperature. Another way for designers to increase circulation is to add pumps to the downcomers. These pumps are called boiler water circulation pumps. Boilers in which they're found are called controlled circulation boilers. Controlled circulation boilers can operate at higher pressures and temperatures than natural circulation boilers of the same size, and as a result can produce more steam for a given size. But regardless of whether a drum boiler operates by controlled or natural circulation, the water flow path is the same. Now, so far we've followed the water from the drum, through the downcomers, into the lower headers, up the water walls, and back into the drum. To complete the water flow path, we need to take a closer look at the boiler drum. This is what a drum looks like from the outside. This is where feed water enters the drum. These are the downcomers. This is where water returns to the drum from the water walls. And this is where steam leaves the drum. Now let's take a look inside. A boiler drum is typically kept about half full of water. Feed water is fed into the drum through this distribution pipe, which runs the entire length of the drum. Heated water and steam returning from the water walls enter the drum and are directed against a baffled section of the drum known as the drum shroud. The shroud directs the water-steam mixture into moisture separators, which separate the water from the steam. The water falls to the lower part of the drum, while the steam collects in the upper part. But the steam still has some water mixed in with it. So before the steam leaves the drum, it's sent to dryers, where additional water is removed. After leaving the dryers, the steam is discharged from the drum through one or more steam outlet pipes. Where it goes from here is what we'll talk about in the next segment. But before we do, review the material we've covered so far and clear up any questions you might have with your instructor. In the last segment, we used this drawing to describe the water flow path through a natural circulation drum boiler. In this segment, we'll look at the steam flow path through the boiler. But in order to do so, we'll have to introduce two other components: superheaters and reheaters. These components act on the steam as it travels between the boiler drum and the turbine. But to understand how they affect the steam, we first need to talk about three important concepts that relate to steam. These concepts are boiling, saturation, and superheat. Boiling is simply the process of converting water into steam. At any given pressure, there is a corresponding temperature at which water will boil. This relationship is such that the higher the pressure, the higher the temperature must be in order for water to boil. The temperature needed to boil water at a given pressure is known as the saturation temperature. The saturation temperature for water at atmospheric pressure of 14.7 pounds per square inch is 212 degrees Fahrenheit. The saturation temperature for water at 1,000 pounds per square inch is 545 degrees Fahrenheit. Now, there's something else you need to know about saturation conditions. Anytime steam and water are present together, the temperature of both the steam and the water will always be the saturation temperature. Let's return to the beaker to make this point a little clearer. Here we have a fairly low flame. Saturation conditions do exist, though. The water is boiling. The temperature is 212 degrees Fahrenheit, saturation temperature for atmospheric pressure. Now we'll increase the flame and produce more heat. You might expect the temperature of the water and the corresponding temperature of the steam to increase, but they don't. All that happens is that the water boils more rapidly. The temperature is still 212 degrees Fahrenheit, saturation temperature for water and steam at atmospheric pressure. The same relationship is true in a boiler. Even though the water in a boiler is at higher than atmospheric pressure and a correspondingly higher saturation temperature, the steam produced in the water walls remains at saturation temperature for the existing pressure. When the firing rate, the amount of flame, is increased, more steam is produced. But as long as pressure doesn't change, the steam stays at the same temperature, and that temperature is saturation temperature. This holds true as long as there is water present with steam. But if there is no water with the steam, if all the water has been removed or converted to steam, then steam temperature can be raised above saturation temperature. This is desirable because the higher the temperature of the steam, the more work the steam can do, and the more efficient the generating unit becomes. Steam that has been heated above saturation temperature is called superheated steam, and it's superheated steam that most boilers produce. Let's see how it's done in a natural circulation drum boiler. You remember we said that in order to superheat steam, the steam had to be free of water? And in the last segment, we saw that steam and water are separated in the boiler drum by moisture separators and dryers. So the steam that's discharged from the drum is in the condition where it can be heated to higher than saturation temperature. This is accomplished in sections of the boiler tubes called superheaters. Superheaters are located in the furnace or in the path of hot combustion gases from the furnace. Superheaters absorb heat and transfer that heat to steam that passes through the tubes. This heat would otherwise be lost out the stack, so superheaters increase the efficiency of the boiler. Superheaters typically raise the temperature of the steam more than 300 degrees Fahrenheit higher than the saturation temperature in the drum. Superheaters are classified in a number of ways. One common distinction is between radiant and convection superheaters. Radiant superheaters receive heat by radiation. That is, they are in direct line of sight of the boiler flame. They can, in a sense, see the flame. Convection superheaters, on the other hand, cannot see the flame. They receive heat by convection. They're heated by the combustion gases rather than by radiation from the boiler flame. Convection superheaters are located a greater distance from the furnace with no straight line path to the flame. They are heated strictly by the heat in the combustion gases. Now, you'll also find superheaters referred to as either primary or secondary. The primary superheater is the one the steam passes through first. It could be either a radiant or a convection superheater, but it's usually a convection superheater. The primary superheater is almost always located in a cooler part of the gas path than the secondary superheater. The secondary superheater heats the steam after it has passed through the primary superheater. It can also be either radiant or convection. Between the two superheaters is a device known as a spray attemperator, sometimes called a de-superheater. Its job is to keep the final temperature of the steam leaving the superheater from becoming too hot. If superheater temperature starts to get too hot, the attemperator sprays water into the entrance of the secondary superheater. This water immediately turns into steam, but in doing so, takes heat from the steam already there, resulting in an overall temperature decrease. Attemperators are only one way of controlling the final steam temperature. Other ways include tilting the burners in the furnace and redirecting the gas flow path with dampers. Often, several methods are used in combination. From the superheater, the steam goes to the turbine. Most turbines have 3 sections: an HP, or high pressure section, an IP, or intermediate pressure section, and an LP, or low pressure section. Steam first goes through the high pressure section, where it gives up some of its energy. In doing so, it cools down and drops in pressure. So, before going to the intermediate pressure section, the steam is sent back to the boiler to be reheated. Reheaters, the second component we mentioned earlier, add more energy to the steam by increasing its temperature. Reheaters work just like superheaters and are classified the same way: primary and secondary, convection or radiant. And like superheaters, reheaters also have attemperators. The reheated steam is sent to the eyepiece section of the turbine, where it again gives up some of its heat and pressure to drive the turbine blades. After the intermediate pressure section, the steam goes through the low pressure section. And finally, the steam is exhausted from the LP section into the condenser, where it's turned back into water. This description of the steam flow path is typical of most drum-type boilers. Not all of them, however, will have superheaters and reheaters. Boilers used in many industrial plants and boilers used just to produce steam for heating may not have superheaters. These boilers produce only saturated steam. And some plants that do have superheaters do not have reheaters. Now, all the material we've presented so far has been centered around drum-type boilers. And as you've seen, the drum serves two important functions. First, it contains a large supply of water for the water wall tubes. And second, it separates the steam and water that have passed through the boiler. But not all boilers work this way. In the next segment, we'll see a boiler that doesn't have a drum. You'll understand it better, though, if you first make sure you know how drum boilers work. So before going any further, review the material we've covered and work the problems in your text. The drum boilers that we've discussed so far are the most common type of boiler used in the power industry today. But they're not the only type. The other common boiler design is the once-through or universal pressure boiler. Both types burn fuel to heat water to produce steam. But as we'll see in this segment, once-through boilers operate in a very different way than drum boilers. Before we discuss how these boilers work, though, we need to introduce a new concept: critical conditions. In our discussion of drum boilers, we saw that at any given pressure, there was a corresponding temperature at which water would boil, the saturation temperature. Well, this relationship only holds true up to a point, and that point is the critical point. It's 3,206 pounds per square inch and 705 degrees Fahrenheit. At pressures and temperatures above this point, there's really no way to distinguish between water and steam. There's no measurable difference between them. They have the same density. This is very important. What it means is that once boiler temperature and pressure have gone beyond the critical point, all the heat produced in the boiler furnace goes toward raising the temperature of the steam. Below the critical point, at pressures and temperatures characteristic of drum boilers, this isn't the case. Considerable heat energy is always used in the process of converting water into steam. The physical change from a liquid to a vapor consumes energy, and it's energy that can't be recovered. It's lost from the system. So boilers operating below the critical point have a built-in inefficiency. But above the critical point, at pressures and temperatures characteristic of most once-through boilers, this inefficiency disappears. No additional heat is needed to change water into steam. Why? Well, because above the critical point, there is no difference between water and steam. They share common physical properties. Water doesn't have to be changed into another physical state. Boilers operating above the critical point are called supercritical boilers. All supercritical boilers are once-through designs, but not all once-through boilers are supercritical. Some once-through boilers operate at subcritical conditions, less than 3,206 pounds per square inch and 705 degrees Fahrenheit. Because once-through boiler designs can operate either above or below supercritical conditions, they're often called universal pressure boilers. Now, when you hear the term universal pressure boiler, you'll know that it's a once-through design, but you'll still have to find out whether it's a supercritical or a subcritical boiler. For the rest of our discussion, though, we'll only be talking about once-through supercritical boilers, since this is the most common once-through boiler design in use today. Once-through supercritical boilers and drum boilers differ in several important ways. First, there is no circulation flow path in a once-through boiler. Water goes through the boiler only once. A very simple way of looking at this is to think of a once-through boiler as a single piece of pipe. Water enters the pipe, is heated by the fire, turns into steam, and then exits the pipe. Another difference between once-through and drum boilers is that because there is no natural circulation in a once-through boiler, the water must be pushed through the boiler, and this is accomplished by a boiler feed pump. Okay, now that we know some of the differences between once-through and drum boilers, let's see how a once-through boiler works. We'll use this schematic drawing. The boiler furnace is here. Water from the feedwater system discharges to a header located at the bottom of the furnace. There is no downcomer. From the header, the water flows up through the water wall tubes that line all four walls of the furnace. As the water travels through the tubes, it becomes hotter and hotter. The water is under a very high pressure, typically around 3,500 pounds per square inch. Remember, this is above the critical point. When the temperature of the water also passes the critical point, the water becomes steam. The section of the tubes where this happens, where water and steam become indistinguishable, is called the transition zone. Since at supercritical temperatures and pressures, all the water passing through the transition zone becomes steam, there is no need to separate the two. So there's no need for moisture separators or dryers. There's also no need for a drum. Remember, the drum in drum boilers is where water and steam are separated. It's also where the water that has been separated out is sent back through the downcomers to be recirculated. In a once-through boiler, this doesn't happen. These boilers get their name because water only goes through them once. There is no recirculation path. After the water has been converted to steam in the transition zone, the steam leaves the water wall tubes and goes to the superheaters. The superheaters in a once-through boiler are essentially the same as those in a drum boiler. They are typically divided into two sections, a primary and a secondary section. And there's usually an attemperator between the two sections to ensure that steam temperature doesn't get too high. The steam flow path is also very similar in both types of boilers. Steam that has passed through both sections of the superheater is sent to the HP section of the turbine. Then there's a reheat cycle for the steam after it leaves the HP section, but before it goes to the IP section. Finally, the steam is sent to the LP section and from there to the condenser. Like any other equipment design, once-through boilers have both advantages and disadvantages. Their biggest advantage is their increased efficiency. Since above the critical point, no additional heat is necessary to change water from a liquid to a vapor, supercritical boilers are more efficient than drum-type boilers. And better efficiency means lower operating costs. But while they're generally less costly to run, once-through boilers are more expensive to build. They need to be constructed of special metals to withstand supercritical temperatures and pressures. Well, now that we've seen how both types of boilers operate, let's look at some of the factors that affect steam pressure. As an operator, you'll be responsible for maintaining the correct pressure in your boiler. Steam pressure in a drum boiler is largely dependent on the firing rate. To maintain a constant pressure, the heat put into the boiler must equal the heat taken out of the boiler as steam. If less heat is added to the furnace, less steam will be produced. If turbine load is held constant, pressure will drop. Conversely, if more heat is added and load is again held constant, more steam will be produced and pressure will increase. In a once-through boiler, the situation is a little different. Heat produced in the furnace has very little effect on pressure. Pressure in a once-through boiler is controlled by the boiler feed pump, which pushes water and steam through the boiler. If load is constant and flow through the pump is reduced, steam pressure decreases. If flow through the pump is increased, steam pressure increases. Lowering the firing rate of a once-through boiler causes only the temperature to drop. Pressure is virtually unaffected. Okay, we've now seen that pressure is controlled by either the boiler firing rate or by the boiler feed pump, depending on the type of boiler. In the next segment, we'll look at another aspect of boiler operation, combustion. First, though, make sure you understand the similarities and differences in water and steam flow paths and in pressure control between drum boilers and once-through boilers. Read through your text and ask your instructor to clear up any problems you might have. Well, so far we've seen that water goes into a boiler and steam comes out. We know that this process uses up energy supplied by the combustion of fuel. In this segment, we'll talk about that combustion process. We'll see how combustion takes place, what's required to get it started, and what's necessary to keep it going. Combustion requires 4 elements: oxygen, fuel, heat, and chemical reaction. All 4 of those elements must be present in the right proportion if combustion is to take place. If any of these elements are taken away, combustion will stop. In a boiler, however, just having combustion isn't enough. We need to control combustion so that it's efficient and clean burning. For this to happen, 2 additional elements are necessary: turbulence, to mix the fuel and oxygen thoroughly, and time to allow the combustion to be complete. This now makes 6 elements that are necessary for boiler combustion: oxygen, fuel, heat, chemical reaction, turbulence, and time. Now, before looking at the overall combustion process, let's see what part each of these elements play in boiler operation. We'll begin with oxygen and fuel. Oxygen is easy. It comes from the air. Fuel can come from a number of sources. The 3 most common fuels are natural gas, oil, and coal. But in order for any of these fuels to burn, they must be able to mix thoroughly with air. For natural gas, this isn't a problem. Gas readily mixes with air. It's a little more difficult to get oil to mix. Oil must first be atomized. That is, it has to be broken into small droplets before it burns efficiently. Coal presents the most difficult problem. In most cases, rock-like chunks of coal must be ground up into granules as fine as face powder before they'll readily mix with air and burn. Once the fuel is in a form in which it will mix with air, it's sent to burners in the boiler furnace. A typical burner has 3 main parts: a nozzle through which the fuel is injected, an igniter to provide the heat source for combustion, and 1 or more dampers called air registers to regulate the amount of air that mixes with the fuel. The burner is enclosed by a wind box which directs air around the burner. Let's now see how the combustion process takes place in a coal-fired boiler. In this drawing, we can see a pulverizer, the wind box, a row of burners, and the boiler furnace. Combustion air is supplied by 2 fans, a primary air fan and a secondary air fan. The secondary air fan is also called the forced draft fan. In this pulverizer, coal enters at the top, and heated primary air enters from the side. The primary air picks up the finely ground coal, dries it out, and carries it to the burners. Secondary air, drawn from the atmosphere by the forced draft fan, is sent to the burners through the wind box. This secondary air, which supplies the additional oxygen necessary for combustion, is directed around each burner through a set of adjustable air registers. In general, whenever a burner is being used, the registers for that burner should be fully open. Coal and primary air entering through the fuel nozzle mix with the secondary air. The mixing of fuel and air is aided by the air registers. They swirl the air, creating the turbulence necessary for efficient combustion. Well, let's stop a moment and see how many of the elements needed for combustion we've introduced so far. In our example, we've provided fuel in the form of pulverized coal. We've furnished oxygen by supplying primary and secondary air, and we've added turbulence with the air registers. We now need to supply heat to start the chemical reaction and time to complete the reaction. The necessary heat is supplied by igniters. Now, there are many different types of igniters, but one common type consists of a miniature oil burner that is ignited by a spark plug-like device. It's located out near the tip of each main burner. During startup, the spark plug provides an electric spark that ignites the oil. The burning oil, in turn, ignites the coal, starting the chemical reaction between the fuel and oxygen. The result, of course, is combustion. Once combustion is started, the burning fuel will usually be all that's needed to ignite the new fuel coming into the furnace, and the igniters can be turned off. In some cases, however, especially at low loads on coal-fired boilers, it may be necessary to keep the igniters burning in order to support combustion. Well, we can now consider the last element, time. The flow of combustible material through the boiler must be slow enough to allow time for complete combustion. Otherwise, combustible materials can build up in the boiler or in the stack, creating an explosion hazard. This is prevented by proper furnace design. The furnace must be large enough to slow the airflow, allowing all the fuel to burn before leaving the furnace. We've now covered the 6 elements of combustion, and we've seen how they fit into the operation of a pulverized coal boiler. Next, we'll compare oil and natural gas burners with coal burners. All burners are pretty similar. The major difference is the nozzles. In this oil burner, the fuel is pumped into the burner and then sprayed out the fuel nozzle, much like water is sprayed out a garden hose. The nozzle in an oil burner is designed to atomize the oil, to break it up into small droplets. In a typical natural gas burner, the gas is fed under pressure from the gas supply to a burner manifold. From the manifold, the gas flows into smaller pipes called gas spuds. Holes in the tips of the spuds direct the gas into the furnace, where it's ignited by the igniters. Natural gas burners are frequently found in conjunction with fuel oil burners, like you see here. Boilers often have 2 different types of burners in case one type of fuel is difficult to obtain. The number, arrangement, and placement of burners varies widely in boilers, so you'll have to check out the specifics of burner arrangement in your plant. You should also know that some burners can be tilted, allowing the flame to be raised or lowered. Raising the flame increases the temperature around the superheater, thereby increasing the temperature of the superheated steam. Lowering the flame, of course, does just the opposite. Now that we've seen how burners work, let's look at a part of boiler operation that'll be your responsibility to control, the fuel-air ratio. Now, this refers to the relative amounts of fuel and air in the boiler furnace. In coal burners, fuel flow is regulated by the coal feeder. In oil and gas boilers, fuel flow is controlled by a regulating valve. Airflow in all 3 types of burners is controlled by vanes or dampers on the forced draft fan, or by controlling its speed. Changing either the fuel flow or the airflow will also change the fuel-air ratio. But How do you know when the fuel-air ratio is correct? You know by monitoring the amount of oxygen going out the stack. If fuel and air could be mixed perfectly, the fuel-air ratio could be adjusted so that exactly the required amount of oxygen was supplied. All the oxygen would then react chemically with the fuel. Unfortunately, this is impossible to do. In practice, to ensure that all the fuel will be burned, we always supply more air than is needed for combustion. This reduces the risk of explosion from unburned combustible material building up in later stages of the boiler or in the stack. Since more air than fuel is supplied to the burner, there should always be excess oxygen going out the stack, oxygen that isn't used up during combustion. Most boilers have an instrument that measures the excess oxygen at the boiler outlet to the stack. Now, you as an operator will use this instrument to keep excess oxygen within a specified range. By periodically checking the meter and by adjusting airflow, excess oxygen will be maintained within the established limits, and the fuel-air ratio will be correct. So far, we've only talked about excess oxygen, but you'll also hear operators refer to excess air. Excess air refers to the air in the wind box, while excess oxygen refers to the amount of oxygen in the gases going to the stack. Now, this may seem a little confusing, but just remember where they are being measured and you'll keep it straight. Air in the wind box, oxygen in the stack. Well, with that, we've come to the end of our discussion of combustion. But before going on to the next segment, read your text and test your knowledge by answering the questions. The greatest degree of heat transfer in boilers takes place in the furnace, where fuel burns at about 3,000 degrees Fahrenheit, or 1,650 degrees centigrade. But heat transfer continues with the production of gases as hot as 2,000 degrees Fahrenheit. In this segment, we'll trace the path of this hot gas, commonly called flue gas, as it goes through the boiler. We'll see what the temperature of the gas is at various stages of a typical boiler. And we'll see how the heat energy in the gas can be used to improve the overall efficiency of a boiler. And finally, we'll talk briefly about some of the pollution control equipment in the gas flow path. Combustion airflow begins here at the forced draft fan. Air and fuel enter the furnace and are ignited. As the fuel burns, hot gases are produced. Some of the heat in the gas is given up to the steam in both the superheater and the reheater. But there's still a lot of heat energy left in the gas. If this heat energy can be recovered before the gas goes out the stack, boiler efficiency increases. Two major components that extract heat from flue gas are economizers and air preheaters. Economizers transfer heat from the flue gas to incoming feed water. Air preheaters transfer heat from the flue gas to the incoming combustion air. Now, let's see how they work. We'll start with air preheaters, of which there are two common types, regenerative and tubular. In a regenerative air preheater, heat transfer is accomplished by means of a rotating metal drum. The drum consists of many small heat transfer segments, each of which is made up of a series of metal plates. The drum is divided in half by a stationary seal plate. Each half is connected to ductwork. We'll remove part of the ductwork so we can see what happens inside. Combustion air passes through one side and hot flue gas passes through the other side. A seal in the middle keeps the air and gas separated. The hot flue gas heats the metal plates. The drum is then rotated, allowing the heat to be transferred to the combustion airstream. In the second type of air preheater, the tubular type, flue gas passes through the inside of tubes. and these tubes are placed in the path of incoming combustion air. The air flows around the outside of the tubes. Heat is transferred from the gas through the tubes to the air. Now, some units have other types of tubular air preheaters that use steam instead of flue gas to heat incoming air. But in either case, the air and the heating medium never come in contact with one another. Economizers work much like tubular air preheaters, except that economizers transfer heat to feed water rather than to incoming combustion air. After giving up heat to the economizer and the air preheater, the flue gas is then sent out the stack. In some boilers, called pressurized furnace boilers, the pressure of the incoming air from the forced draft fan is enough to push the gas out the stack. But in other boilers, discharge of gas out the stack is helped along by an additional fan called an induced draft fan, or simply an ID fan. Boilers with both forced draft and induced draft fans are called balanced draft boilers. The flue gas in both pressurized furnace boilers and balanced draft boilers contains potentially harmful byproducts. Some byproducts, like sulfuric acid vapors, can be very corrosive. If flue gas temperature gets too low, these acid vapors will begin to condense and can seriously damage vital boiler parts. To prevent this, the temperature of the flue gas leaving the boiler is kept above the dew point, the temperature at which vapors in the gas will begin to condense. In this way, the risk of corrosion is reduced. Flue gases can damage not only the boiler, but the environment as well. Particles and gases that are in the flue gas as byproducts of combustion are potential sources of air pollution. These particles and gases must be removed or greatly reduced in concentration. Two commonly used devices for removing these pollutants are precipitators and scrubbers. Precipitators generally remove particulates, such as ash particles, from the flue gas. Scrubbers remove both particulates and gases. The way these devices operate will be covered in the environmental protection topic. For now, you only need to know where they're located and what in general they do. These devices are all located in the flue gas path to the stack, and their purpose is to remove particles and to clean gases that would otherwise create air pollution. Well, we've now covered the major components in the air and gas flow path. Let's now review those flow paths. Now, as we do, we'll indicate some typical temperatures in various parts of the system. Now, keep in mind, though, that the temperatures in your plant may be different. The airflow path begins at the forced draft fan. Air enters at about 90 degrees Fahrenheit. The temperature of the air is increased to 500 degrees Fahrenheit as it passes through the air preheater. The air then enters the burners, where it mixes with the fuel. The fuel-air mixture is ignited and burns at about 3,000 degrees Fahrenheit. Flue gases at about 2,000 degrees Fahrenheit are produced as part of the combustion process. This gas continues through the boiler and reaches the superheater area at about 1,800 degrees Fahrenheit. It leaves the superheater at 1,200 degrees Fahrenheit and enters the reheater area. The gas leaves the reheater at 800 degrees Fahrenheit and passes through the economizer, exiting at about 650 degrees Fahrenheit. The gas loses about 350 degrees in the air preheater and finally exits up the stack at 300 degrees Fahrenheit. The heat transfer processes which cause these temperature drops will be discussed in great detail later. For now, it's important to understand that heat energy is transferred to water, steam, and air in the boiler. And it's important to know the different flow paths in the boiler. With that, I think we've come to a good stopping point, so turn off the tape and review the air and gas flow paths in your text. You may also want to find the air and gas temperatures in your boiler. If you have any problems, ask your instructor. Now that we've seen how a boiler works, we're ready to talk a little bit about what you, as an operator, do to run the boilers in your plant. Now, since we're just beginning the Power Principles program, we'll stick to the basics here and just give an overview. One important job you must be able to do as an operator is to maintain proper level and flow in the boiler. While this is normally done automatically, it doesn't mean that you don't have anything to do. It's up to you to monitor the operation of the automatic control systems. And automatic systems sometimes fail. If that happens, you must be able to analyze the situation and take the proper manual actions to maintain proper level and flow. One example of automatic control is water level in the drum of a drum-type boiler. Water level is displayed and recorded on charts, meters, and gauge glasses. Almost every operator experiences a time when something goes wrong with an automatic system. Drum level may drop when it should be increasing. If this happens, level must be restored by transferring the feedwater pump controller or the feedwater valve controller from automatic to manual. This will allow flow to be adjusted by the operator. Not until level is returned to normal and the problem is corrected should control be returned to automatic. An important part of your job will be monitoring drum level and other automatic control systems, looking for trends that could indicate a problem. And unless you understand how the boiler is designed to operate, you may not know what the automatic systems are controlling and what to do if a problem develops. You, as an operator, must learn all the processes that go on in the plant. And you must know what to do to keep all the equipment operating properly in either automatic or manual control. Another aspect of boiler operation that requires careful operator attention is draining and venting. Various parts of the boiler have drains, vents, and blowdowns. Vents, like this boiler drum vent, are located on top of a component. They're usually opened only during startup when there may be a lot of air in the system. They should be closed as soon as steam comes out. Drains like this water wall drain are located on the bottom of components. They're usually opened only when the component is shut down. Otherwise, the natural circulation flow could be upset, causing the boiler tubes to overheat. Some drains, though, like this superheater drain, should be opened when starting up the boiler. During startup, steam flow through the superheater is very small, usually not enough to keep the superheater tubes cool. The heat problem is solved by opening the superheater drains. This increases flow to keep the superheater from overheating. It also helps get rid of any water that may have condensed and collected in the superheater. Now, in addition to draining and venting, you'll also have occasion to blow down the boiler. Blowdowns are a type of drain that are opened during boiler operation. One very common blowdown on a boiler is called a surface blowdown. It's located near the normal water level point in the boiler drum. It's opened periodically during operation to remove contamination that builds up in the drum. In future topics, we'll see why contaminants tend to build up in this area of the drum. For now, though, let's turn our attention to another routine operation, soot blowing. During operation of most boilers, but coal-fired boilers in particular, soot, a byproduct of combustion, builds up on the water wall tubes in the furnace. The buildup of soot blocks effective heat transfer. Soot blowers are designed to remove soot by blowing off the tubes with a cleaning medium of compressed air or steam. A typical soot blower is made up of a lance tube with nozzles, a feed tube, and a valve. When the valve is open, the cleaning or blowing medium is sent through the feed tube and is discharged out the nozzles in the lance tube. Soot blowers are of two general types, retractable and fixed. Retractable soot blowers are motorized to allow the lance tube to be inserted into the furnace while soot blowing is in progress. When the soot blowing operation has been completed, the tube can be retracted and thereby protected from the extremely high temperatures in the boiler. Fixed soot blowers, the second main type, are mounted on the boiler with only the lance tube permanently projecting into the furnace. Because the lance tubes of fixed soot blowers are always exposed inside the boiler, they're usually found where the temperatures are relatively low. The soot blowing operation is initiated in the control room. Blowers are typically programmed to operate in a certain order. Although soot blowing is controlled automatically, there may be times when you have to manually bypass a certain blower or manually retract a blower that doesn't respond to automatic commands. As with other situations of this kind, the more you know about how soot blowers are supposed to work, the better prepared you'll be when you have to take manual control of the operation. All the operations we've described so far are usually performed in the control room. The control room is the heart of the plant. It's also where many of the most important meters, charts, and alarms are located. It's your responsibility as an operator to carefully watch all the information being displayed. If an alarm sounds or a meter or chart shows an abnormal reading, you must know the proper response. The plant and plant personnel could be seriously harmed if you don't respond quickly and properly. Knowing the right thing to do requires a lot of study, thought, and experience. The important thing now is to keep at it. And remember, the more questions you ask, the more you'll learn. Now, in this unit, we've now seen how water circulates through a boiler, how steam is generated, and the path steam takes from the boiler to the superheater, turbines, and reheater. We've looked at each of the 6 elements of boiler combustion: fire, oxygen, heat, chemical reaction, turbulence, and time. We followed the path of hot gas through a boiler and got an idea of how vents, drains, and blowdowns are used. Well, this might be a good time to go into your plant's control room and see what goes on there. But first, read the text and answer the questions. Don't forget, if you have questions, discuss them with your instructor.